Hello again. Welcome to Algebra, March 18th. Today we're going to talk more about systems of equations and how we graph them and what they mean. But first, the daily challenge. Comment in the field if you could tell me what my shirt says. It's kind of poignant as it pertains to the current events. All right, now for our lesson. So I asked you guys to work on graphing systems of equations with IXL strand U.2. That was posted yesterday. Please try to have that done as soon as possible. I know some of you did it, I saw already. Some of you had done it in summer work, which also will count. And I think the average time it took was like maybe 15 minutes. So let's talk about when the equation is not already given to you in slope-intercept form and what we do there, as well as the two special cases. So our first example will be, let's say we have negative 2x plus 4y equals 6. And we also have an equation x minus y equals negative 1. Both equations currently written in standard form, but we have to put them into slope-intercepts so that we can graph them. So in the first equation, I would add 2x to both sides, and that would give me 4y equals 2x plus 6. Then I divide everything by 4, and I get y equals 1/2 x plus 1.5. You can call that 3/2 or 1 and 1/2, it does not matter. And then for the second equation, a little easier because it's a little less complicated, we're going to subtract x from both sides, and I get negative y equals negative x minus 1. I don't want to graph negative y, so I have to divide everything by negative 1. And that turns all the signs. Y equals x plus 1. All right, we have two equations, and now we can graph them to see what we get. Again, I'm using hand-drawn graphs, so bear with me on this. The first one has an intercept of 1.5. Just go up and down by 4 and across in both directions by 4. So we have 1.5 is our y-intercept. Going to rise 1, run 2, which should at this point not be an issue for you guys. I'll do it again just to see what the line would look like. And I get a line that looks something like that. The second equation, y equals x plus 1, it shouldn't be too hard to graph. Positive 1 is the y-intercept, and it has a slope of 1, so rise 1, run 1, and you can do it again and again if you like. It looks like that's what the line would be. So I see right over here the place where the lines are crossing. Now I'm going to make my best guess that that coordinate is 1, 2. So my question is that actually the place where they cross? Is that the solution? The only way to tell is to plug it into both equations and see if it works. So if we plug it into the first equation, we get, I'll just use this. When I plug that in for x and y, does it work? That's really the question. So does 2 equal 1/2 times 1 plus 1.5? If that works, we'll have the solution. I have 2 equals 1/2 plus 1.5, and hopefully you guys can see that 2 does equal 2. So that worked for that line. The other one, again, should be pretty easy. Let's plug it in right here and squeeze it in. Does 2 equal 1 plus 1? Well, yeah, it does. So for both lines, the coordinate worked, and that makes it the solution to our system. So that's another example of how we're going to solve with graphing. In this case, unlike yesterday's video, where the equations were not already in slope-intercept form. Now, we're going to move on to special systems. A special system is one where the lines might not just cross one time, they might cross forever, meaning they're the same line, or they could be parallel lines where they don't cross at all. So let's take a look at the special cases, make it nice and fast. The first special case will have y equals 2x plus 3, and also the equation negative 2x plus y equals negative 1. Now, as you can see, this first line is already in slope-intercept. Second one is not. So I'll put it in slope-intercept so that I can then graph it. Again, I have to add 2x to both sides. And I get y equals 2x plus 1, and that's handy. At this point, you might notice that the slope in this line and the slope in that line are the same. You also might notice that they have different y-intercepts. Hopefully you remember that when two lines have the same slope, but different y-intercepts, they're parallel. And parallel lines do not cross. But let's just graph it, and we'll see how that looks. The first line has an intercept of positive 3 and a slope of 2. So I'm just going to graph, again, a hand-drawn graph, just to roughly sketch what this will look like. Positive 3 is the y-intercept. It has a slope of 2, means it rises 2 and runs 1. And that's roughly what my line looks like. My second line, as you already know, has the same slope, but a different y-intercept. So negative 1 is the y-intercept. And it also rises 2 and runs 1. And it looks like that. From the graph and from the equations, hopefully we can see that they actually are parallel and they will not cross. So what we say here is that there is no solution, because again, a solution is the place where the lines cross. Parallel lines have no solution. If they were given to you in slope-intercept, it's very easy to see if they have the same slope but a different y-intercept. But if they weren't, put them in y-intercept and then you'll see. You don't really need to graph it if you can tell by the equation that they already are going to be parallel lines. The other special system is the one in which the lines cross everywhere. There's only one way for that to happen. They have to be the exact same line. So they'd be the exact same equation if you put it into slope-intercept form. And here's an example for you. So I'll give you two lines. We have x plus 2y equals 4. And we have y equals negative 1/2 x plus 2. Again, I gave you one in slope-intercept and the other not, and that's fine. First, I'll take this equation and I'll put it in slope-intercept by subtracting x from both sides. 2y equals negative x plus 4. Then I have to divide everything by 2. So y equals negative 1/2 x plus 2. The other equation was already y equals negative 1/2 x plus 2. Ideally, at this point, you wouldn't have to graph it, but because this is the beginning of the unit, we will, and we'll see what it looks like. Clearly, you can see they are going to be the same exact line, but that's okay. We have an intercept of positive 2. We have a slope of negative 1/2. Let's see what that looks like. Well, positive 2 is here. Negative 1/2 means go down 1 and go over 2. If you wanted to do it again, you certainly could. My hand-drawn graph is a little loopy, but that's okay. The second equation, which, as you already know, is identical to the first, will have the same y-intercept right here and the same slope down 1/2. It's the same line. So we could just draw these other arrowheads to indicate that it's the same place. What you're going to say here is that they have infinite solutions. You could spell out infinite solutions. You could use the infinity symbol if it helps you. In any case, all it means is those are the same lines, and therefore they cross everywhere. There are only three kinds of systems with linear equations. The ones that cross one time, where there is a given solution, which is the coordinate where they cross, or the parallel system where they never cross, or again, the infinite solution where they are the same exact line crossing everywhere. That's today's lesson. Now, what I'd like you to do is IXL, again to about 90%, but this time the strand is U dot 4. Here we go. U4 on Algebra 1 tests whether you can tell how many solutions there will be based upon the equations and graphing. Thank you.